In this lecture, we start by talking about partition of a sample space. So consider a set of events E1, E2, E3, E4 all the way to En such that they do not share any elements in common. So for any two events Ei and Ej, their intersection is null set. For example, E1 intersect with E3 would be null set, E2 intersect with En would be null set, and so on. And their union is the entire sample space omega. So we call this set of events as partition of omega. So all these sets are mutually exclusive, or you can say disjoint, but their union forms the entire sample space. So let us see figuratively. So you say you have this entire sample space omega, and then you have a partition into a bunch of sets. So say for this example, we have events E1, E2, E3, E4, E5, E6, E7, E8. So all of them are disjoint, they just share the boundary, but all of them also cover the entire sample space omega. So if I take union of E1 to E8, it will be omega, but intersection of any of these two sets is empty. So this is partition of omega. So for any two events A and B, you can partition set A in terms of set B. So let us see this. You have the entire sample space is omega, and you can write this set A as the disjoint union of A intersection B union A intersection B complement. So A intersection B is this small portion right here, which we have colored in green. So this is a part of set A, and A intersection B complement is this portion in yellow. And so we see we were able to write this set A in two pieces, A intersection B union A intersection B complement, and both of them are disjoint. So you can say probability of A is equal to probability of A intersection B plus, you can say, probability of A intersection B complement. And then we use conditional probability formula. You write probability of A intersection B as probability of A given B times probability of B. So recall that the formula was probability of A given B. You defined it as probability of A intersection B over probability of B. So now we are writing for A intersection B, we are writing this. Similarly for A intersection B complement, we write probability of A given B complement times probability of B complement. So this is nothing, you just put complement, complement, and complement here, and so you get probability of A intersection B complement is A given B complement times probability of B complement. So this is an important formula. This is also called Bayes formula. Or you can say Bayes' formula. And this is used multiple times in the entire course of probability, so you need to remember this. Now you could, instead of just having B, you could disjoint A into large number of other sets. So now we have just B here, but you could cover A with large number of other sets. So say you have set A, it could be covered by a large number of other sets, say E1, then you might have E2, E3, or then you might have E4, and these sets might also intersect with each other. So in that case, you can write a more general formula that probability of A is summation of I equals to 1 to n probability of A given this event EI times probability of EI. So that is it. Just to recall, this was your set A, which you have covered with say 4 sets here: E1, E2, E3 and E4. Now let us give an example where we actually use this Bayes formula for computing probabilities. So this is a standard example and it shows up in many formats. So we have modified it for finance. So say you hire 2 analysts, or you get recommendation from a company which has 2 analysts, and these 2 analysts make investment recommendations. So they recommend you what investment you need to make. So analyst 1 makes bad recommendation 20% of the time, but analyst 2 makes bad recommendation only 5% of the time. But it is also true that analyst 1 gives twice as many recommendations compared to analyst 2. So he is more productive, but he also makes bad recommendations 20% of the time. So suppose you acted on a recommendation. You do not know whether this recommendation came from analyst 1 or analyst 2. We want to compute the probability of the recommendation being satisfactory. So again, you have 2 analysts. Analyst 1 makes bad recommendation 20% of the time. Analyst 2 makes bad recommendation 5% of the time, but analyst 1 is twice as more productive as analyst 2. And we want to compute the probability of a recommendation being satisfactory. You do not know from where the recommendation came from, whether it came from analyst 1 or analyst 2. So you put A as the event that recommendation is satisfactory, and B is the event that it came from analyst 1. So again we will use Bayes formula right here. Copy this here. So probability of A given B times probability of B plus probability of A given B complement times probability of B complement. So first, what is probability of B? So event that it came from analyst 1. So analyst 1 is twice as productive as analyst 2. So if there are 3 recommendations, 2 will come from analyst 1 and 1 will come from analyst 2. So probability of B, that the event that it came from analyst 1, is 2 by 3. So 2 out of 3 recommendations. And B complement is, obviously there are 2 analysts, so if it did not come from analyst 1, it has to come from analyst 2. So B complement is did not come from analyst 1, or it came from analyst 2. So it came from analyst 2 means it is 1/3. So probability of A given B. So event that recommendation is satisfactory and it came from analyst 1. So this will be 80%. So satisfactory recommendation coming from analyst 1 is 80%. So bad recommendation is 20%. So that means satisfactory recommendation is 80%. So 80% is 0.8, and instead of 0.8 we write 4 by 5. Now probability of A given B complement. So recommendation is satisfactory. B complement means it came from analyst 2. So satisfactory recommendation came from analyst 2. So that comes with 95%, because this person makes bad recommendation 5% of the time. So 95% of the time he makes good recommendation. So instead of 0.95 we write 19 by 20. So you now just do the algebra, you get 51 by 60. So this is the probability that your recommendation will be satisfactory. So you get the recommendations from analyst 1 and analyst 2. So the probability that it will be satisfactory is 51 by 60. Now suppose the recommendation you got turns out to be bad. So the probability that it came from analyst 1. So B is the event that it came from analyst 1. Given that A complement is recommendation is bad, because A is the event, recommendation is satisfactory. So A complement is the event, recommendation is not satisfactory, or you can say bad. So we want to find probability of B given A complement. So you just use the formula of conditional probability of B intersection A complement over probability of A complement. Now you use the formula again. So probability of B intersection A complement would be probability of A complement given B times probability of B. So again, this comes from the fact that you are saying probability of A complement given B is probability of A complement intersection A complement intersection B divided by probability of B. So instead of probability of A complement intersection B, you could write probability of B intersection A complement, and then you multiply these two. So you get probability of B intersection A complement is probability of A complement given B times probability of B. Now probability of A complement given B, so that is recommendation is bad and it came from analyst 1, because B is it came from analyst 1. A complement is recommendation is bad. So analyst 1 makes bad recommendation 20% of the time. So 0.2 you can write as 1 by 5. So that is what this portion is done. Now probability of B is 2/3. The recommendation came from analyst 1, that is probability of B, it is 2/3. So that is what, because 2 out of 3 recommendations come from analyst 1 over probability of A complement. So probability of A was 51 by 60. So probability of A complement is 1 minus probability of A, and that's what we write here, 1 minus 51 by 60. So that is 8 by 9. So if the recommendation turns out to be bad, the probability that it came from analyst 1 is 8 by 9.